Hello everyone. In today's tutorial, we're going to see how to take the Altera 50 megahertz clock and divide it down to a 1 hertz clock. In a previous tutorial, I covered how to make a divide by 2 circuit and divide by 5 circuit. So I've pulled those block diagram files from another project, from that previous tutorial, and put them in a folder called 1 hertz clock. Right? I'm just going to starting Quartus here. We're going to create a new project. File, new project wizard. Right. And I want to choose the folder, this folder that I put out on my desktop, which I called 1 hertz clock. All right. Name of the project, I'll also call it 1 underscore hertz underscore clock. Next, we could go ahead and add in these files. I'm going to add in the divide by 2 circuit. So I'll just do that now at this point. Hit next. I'm going to use the defaults right now for simulation. We'll eventually put it on the board. We choose Model Sim Altera, Verilog HDL. Next, and finish. So I use the default chip. We will put it on a board soon. I just want to open up then. I forgot the add button evidently when I selected it. Never fear. I'm just going to say, let's open that up. Put it here. Right, now that it's here, I can go to project, add current file to project. It becomes part of the project environment. All right, so this divide by 2 circuit, it's also a modulus 2 counter. What we want to do is we want to have an input reference clock. Here's our input reference clock. Let me make this a little bigger here. All right, our input reference clock, right? I've got a reset attached to this D flip-flop. We created this circuit with a D flip-flop. When we took a look at the state table before, right, we said we want a divide by 2 counter. It's actually a state machine that cycles from 0 to 1, back to 0, back to 1. Right, so in our present state, if we create our state table, when our present state is 0, our next state should be 1. When our present state is 1, our next state should be 0. We can derive a state equation from this. We look at the next state, and using a D flip-flop, right, we know that, let me turn on the text tool. We can say that our input to our D flip-flop should be what Q next is, or Q next state. Right. And if we look at this column, this is simply Q naught. Right. That's where that comes from. Right. And so if you look at the circuit we derived before for our divide by 2, we have our D flip-flop, we have our input clock. We take then the output Q, we run it through a NOT gate and feed it back in here to D, right? The external output of our circuit is called, I named this label mod 2 clock, right? And we also have the reset on here. We worked with the circuit in the previous tutorial, but let's just go ahead and run a simulation to make sure that it's still working, that I haven't done anything to hurt it, change it since last time. So I just save that. I'm going to click on analysis and synthesis here. And of course, I forgot to change my top level design entity. Remember, I named the project 1 hertz clock. It looks to that to be the top level by default. If I simply right click on this and say set as top level, now if I run analysis and synthesis, we won't get that top level error. Right. While that's running, we're done. We got our typical warning. I don't have parallel compilation enabled, and that's okay. I'm going to go to File, New. And I'm going to pick then this university program vector waveform for simulation. Right. Pops this up. Let's set the end time to, maybe I'll just make it 100 nanoseconds. Okay, I'm going to go here, insert node or bus. Right. Node finder. It's popping up all my menus on the other screen. List, there are my 3 signals. put them into here, say okay. All right, now we've got, I like to have my output down here. We'll move reset up here. I'll set reset high for right now. I'm going to set my clock at 10 nano should be okay. All right, and what I'm going to do then is for this first time period here, I'm going to select this. I'm going to assert reset. So the Quartus D flip-flop that I've used has an active low reset. It's actually an asynchronous reset as well, but active low means that when reset is 0, we should see the 0 being the output of our flip-flop, right? Otherwise, for the rest of the time, reset will be high, so we won't be resetting the circuit, so we should see the divide by 2 clock behavior. Right. So if we save this now, right, I'm going to call this divide by 2 sim. Run the functional simulation. Let's open this up. All right, so here from 0 to 10, when reset is low, notice the output of our counter here is 0, as we'd expect. Now when reset goes high, let's take a look. This D flip-flop is rising edge triggered. So let's see, on this first rising edge here, then we see that our clock as well, since the output of the flip-flop was 0. All right, if we pop this circuit, let's take a look at our circuit. All right. So here we can see that if the output of the flip-flop is 0, well, as it goes through the NOT gate, out here waiting on D is 1. So 1 was waiting to be clocked through. And here, let me bring this back to minimization here. Meaning on this rising clock edge, since the output of the flip-flop was 0, 0 not is a 1, so our clock goes to a 1. And it stays at a 1, right, until the next rising edge of the clock. And on that next rising edge of the clock, the flip-flop output Q was 1. Q naught is a 0. That's when the 0 gets clocked through, right? And so you can see, right, if we come back starting here, here's 1 complete clock cycle, 2 complete clock cycles. So between 15 nanoseconds and 35 nanoseconds, we have 2 complete reference clock cycles and 1 complete output derived clock cycle. Right, so we call that output clock our derived clock, the input clock the reference clock. So we can see that our divide by 2 circuit, if you follow the rest of the simulation, it's working. Right. So we verified that that behaves as we expect. We could put some notes in here if this helps as well. We could say that this is the derived clock. This is the reference clock, right? And what it does is it counted 2 clock pulses. That's what a divide by 2 or a mod 2 counter does. All right. And the other circuit we're going to need as well is I'm going to open up the divide by 5 that we made in a previous tutorial. All right, the divide by 5 is a more complex circuit. Let me just add it to the project. Okay, I'm going to remove the divide by 2 from the project. I'm going to make divide by 5 my top level entity. So this mod 5 counter, right? What I've done here is I've made some notes in the schematic for myself. The state table for the mod 5 counter, right? We want to count 5 clock pulses. And we need 3 flip-flops to do that, right? And we have some unused states when we develop that counter, right? We use states 0 through 4, but we didn't use 5, 6, and 7, right? We just wanted, after a count of 4, to reset back to 0. Remember that count goes 0, 1, 2, 3, 4, back to 0. So you can see here when our present state is 0, our next state is 1. When our present state is 1, our next state is 2. When our present state is 2, our next state is 3, and so on. Here, when our present state is 4, we go back to 0. And this circuit will count 5 clock pulses, right? It's a mod 5 counter. What we found when we derived the circuit, though, is we didn't get a nice 50% duty cycle. If we just use these 3 flip-flops, so let me scroll over here in the circuit. So these 3 flip-flops, D0, D1, and D2, we made this a synchronous counter, meaning each one of these flip-flops is driven by our reference clock. Right? And we came up with equations then for D1, D2, D0. When we ran that simulation, we found out we did have a mod 5 counter, right? We counted in that cycle, but we didn't have a 50% duty cycle, right? The problem is we don't have a nice even division by 2, and we have positive edge triggered flip-flops. We found that we needed a negative edge triggered flip-flop, right? We took a look at Q1, and we saw that Q1 was producing a 40% duty cycle. Right. We actually used a formula to help us find that. And the formula was, I'm trying to turn this on, but all right. So T equals 5, right? The count. And we said we want to take T minus 1 and divide it by 2. And so that gives us 5 minus 1 divided by 2, which equals 4 divided by 2, which equals 2. Wow, I can't do basic math today. And what this did is this number 2 said we need to look for a flip-flop where we have 2 consecutive 1s. Right? Well, we only have 3 flip-flops. When we took a look at Q2, we only have one consecutive, or we only have one 1. Q0 has 2 1s, but they're not consecutive. Q1 has 2 consecutive 1s. And that's where we found then that this would produce a 40% duty cycle, right? Because 2 out of 5 times it's high, 3 out of 5 times it's low. And the duty cycle is the amount of high time in the period. All right, so we had that 40% duty cycle. And we took a look at that simulation. We said, well, if we could have a negative edge, we needed to actually have a negative edge trigger at 2.5 halfway through. So 2.5 of our reference clock time, right? 2.5 out of 5. So what we did was we added then this additional flip-flop. Remember, these are positive edge triggered by default. In order to make it negative edge triggered, we went ahead and inverted the clock signal, right? And we fed Q1 into this. The reason we fed Q1 into this is Q1 was a flip-flop that was producing that 40% duty cycle. When we then negative edge triggered it, what we got out was we got out another 40% duty cycle, but it was shifted just that small half a clock period, which then we discovered when we combine the two. So here we combine the two, we OR them together. That provides the divide by 5 output, right, with a 50% duty cycle. And let's see, I just went back there and saved the text that I had added the other day. All right. So what we want to do now is we want to confirm that this circuit still works. I did set that as a top level entity already, I believe. Let's just go ahead and do analysis and synthesis on it. I can get ready to run a simulation on it as well. All right, so file new. Let's pop up a new simulation. Made 120 nano. Let's bring in all those signals. All right, so I'm only bringing in the divide by 5. I'm not picking up any of the count numbers, because all we're trying to do in this circuit is get the clock division. Right, so if I move reset up here, we're going to assert reset as high. Let's just take a look at what happens with the clock. Let's see, I'll make the clock 5 nanoseconds. Save the file, divide by 5 sim, and let's run our functional simulation. So let's take a look at this point here. Right. So we don't have our perfect clock, right, when this starts out. What we have is right here, starting at 7.5 nanoseconds on this rising edge, we have 1, 2, 2.5 reference clock cycles, but a half of an output clock cycle. And then as we finish, here's the other 2.5, 1, 2.5. Here's our low, our other half of our output cycle. So you can see between 7.5 nano and 32.5 nano, we have a divide by 5 clock, right? We have 1, 2, 3, 4, 5. 5 complete reference clock cycles, 1 output clock cycle. And that works all the way across here as well. So there's our divide by 5 clock. I didn't set the reset. If we wanted to, we could go ahead here and confirm that the reset's working as well. Just in this period, I'll set it low. Control S to save it, run the functional simulation. Again. And now we see that our clock starts over here. So reset, right? Well, the reset is low. You can see that all we're getting out of this circuit is a 0, which is what we should be getting, all zeros out of all the flip-flops. Right? It completely resets the output to 0. Otherwise, now when we check our divide by 5 clock here, starting at 17.5 nanoseconds, here is where we start getting our divide by 5 clock division. All right, so we confirmed that the reset works as well on this circuit. Right. Now that we have both of these circuits, right, we're going to make a divide by 10. I'm going to open up the divide by 2 again. I'm going to add it back into the project. All right. And so now to make a divide by 10, I'm just going to cascade these two together, right? 10 divided by 2 gives me 5. 5 divided by 5 gives me 1. So I want to go from, I want to use 10 reference clock cycles to have 1 derived output clock cycle, right? And I need to make block symbols out of these. So with this one selected, file, create update, create symbol files for current file, right? Yes, I want to keep the same name and store it in the main project folder. Created that, and then same way for divide by 5. File, create, update, create symbol files for current file. Just put that block symbol, BSF, block symbol file. Right, that created that, put it in my project folder. Let's make a new schematic. And now let's insert here. All right, so out in our project folder, now we have our divide by 2 and our divide by 5. Doesn't really matter first whether we divide by 2 and then by 5, or divide by 5 and then by 2. Our main goal is to get that divide by 10 circuit. And let's put the divide by 5 symbol on. Cascade them like this. We're going to need that input reference clock, right, and reset as well. We'll have a single output here, or divide by 10. And so our reference clock, let me make that bigger so you can see what I'm doing. Right click on that. I'm going to name that clock, right? Here's my input reference clock. This will be reset. I'm going to tie both of the resets are tied to the same input. The clock then is tied to our first input, but the output of this divided by 2 becomes the input to the clock here. So that effect just ripples through. Oop, I accidentally chose a bidirectional pin instead of an output pin. We don't want that. Let me delete that. And let me grab output. Right, we only want output. We don't want output input. Let's wire this. All right, let's name this then output divide by 10. All right. Now we could have made a divide by 10 counter, but since we already had a divide by 2 and a divide by 5, why not use them, right? Especially since we're just going really for functional simulation here and not worried about efficiency of number of components, timing, right? We just want to get this up and running. Check its functionality. All right, so I need to save it. All right, and I want to call this divide underscore by 10. All right, that block diagram file in my project folder. I want to make this the top level entity. Now I need to make sure that the divide by 5 and divide by 2 are part of the project because the divide by 10 depends on them. Right, and let's run analysis and synthesis here before we run our simulation. All right, so here's our new simulation. Yeah, 120 now should be fine. Let's insert our signals. So just for the first test, I'm going to set reset high the entire time. I'm going to set my clock. Now let's go with 5 nanosecond period. Let's save this as divide by 10 sim. And let's run the functional simulation then. All right, so let's take a look here. All right, so at 12.5 nanoseconds, here starts my divide by 10 clock. So one output clock, one complete cycle goes here from 12.5 to 62.5. All right, and let's count. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 reference or input clock cycles to one derived output clock cycle, right? And it continues on that way throughout the simulation. It looks now like we have our divide by 10 clock that we wanted. And if we wanted to test to make sure that the reset was working, right, I could just select some sort of time period, either here at the beginning, I can assert reset to low, Control S to save, run the functional simulation again. And now we can see that while reset is low, the output here is low. And our divide by 10 clock then actually doesn't start right until 22.5 nanoseconds, right, where we start getting that nice 50% duty cycle. Well, we got the behavior that we wanted. Excellent. Right. So our ultimate goal in this is I said we were going to right? The title of this was 50 megahertz to 1 hertz. Well, if we look at the Altera system clock, it is a 50 megahertz clock. So what we want to do now is we want to actually then use this divide by 10 and our divide by 5 to start dividing 50 megahertz or 50 million cycles per second down to 1 cycle per second. Let me make a block symbol out of this. File, create update, create symbol file from current file. All right, created that. So now let's make a new schematic. And I'm going to go ahead and divide by 5 first in this circuit. So I'm going to insert, then from the project, I'm going to insert 1 divide by 5 here. And I'm going to have our reference clock input. Let's see. I'm going to give this the long name of reference clock. And sorry, let me make that bigger. All right, reference clock. And when we get to the hardware level, we're going to tie Altera's 50 megahertz clock to this reference clock signal. Right. Now we're going to need a reset eventually, but let's go ahead now. And when we get something out of this divide by 5 here, what we're getting out is actually then, so let me, if I put in a 50 megahertz reference clock, if I divide it by 5, then what I have here is a 10 megahertz clock. And now if I insert another symbol, I divide by 10 symbol, and now if we wire these together, didn't want to do that. If we wire these together, now we have this 10 megahertz clock input here. And coming out, we'll have a 1 megahertz clock. Let's grab the text tool again and show that, well, here, right, now we have a 10 clock. Here, we have, if we divide 10 megahertz, now we have a 1 megahertz clock signal, right? And we're going to keep dividing this until we get down to 1 hertz. All right, so let's put in, oh, sorry, I still got the text tool on. Let's insert. Repeat insert mode. So if I divide 1 megahertz by 10, I get 100 kilohertz, 10 kilohertz, 1 kilohertz, 100 hertz, 10 hertz, 1 hertz. I think that's enough of what I need. We could cascade these side by side. Yes, so here, once again, if we now wire these together, go back to the text tool here and put a reminder. Now, this is a 1 megahertz clock, but coming out of here, we have well, 1 megahertz, 1 million divided by 10 gives us 100K hertz clock. And we go back to wiring here. If we go back to this, here and here. Right, again, grab the text tool to remind ourselves that here we have 100 kilohertz clock. Here we have a 10K hertz clock. Similarly now, here we have that 10K hertz input. So here we have the divide 10K by 10. We have the 1K hertz output. Back to wiring tool. This is why I like Verilog. I don't have to wire all of this, but this helps me visually understand what's going on. All right, so 1K hertz coming in here. Right, again, as a reminder, let's just write some text there. 1K hertz. And coming out of here, we're going to have, well, 1,000 divided by 10 is going to give me 100 hertz. So 1,000 divided by 10 gives me 100 hertz. I've now got 100 hertz here for input. 100 divided by 10 is going to give me 10 hertz. So here we'll have 10 hertz, right, which gives us 10 hertz input down here. And finally, oh, I was short one. Yes, I was short one. We need one more. Divide by 10 here. So I need to turn off the text tool to get the other menu. One more divided by 10. So 10 divided by 10. Oh, I didn't need that. It gives me the 1 hertz signal. All right, see what happens when I don't finish? Because if I were to divide that down again, now I'd have 1/10 of a hertz, and I don't want to go that far, right? Our goal was to only go down to 1 hertz. Oh, didn't mean to do that. For some reason, okay, I thought I turned that on here. All right, there's our 10K hertz output. Now I want to save my work. It's a good idea to save as you go along. Should have saved sooner just in case anything bad happened. All right. Just going to go ahead and call this my 1 hertz clock. Yeah, I can call it that. All right. And it needs an output. So if all I want to do is grab then this last signal, right, I could easily do that. This thing appears to be a little bit. All right, 1 hertz clock. And I hadn't wired in reset. We could add, and then the reset as well if we want. So we need another input pin for that. Name that reset. And let's wire all the resets together. All right. Now, here's the thing. We really can't run a functional simulation of this. Our simulator, the built-in university vector waveform simulator, won't run long enough. We haven't learned how to work with test benches or other simulators and to set things in picoseconds. What we're going to do is we're just actually going to end up putting this on the board and seeing if we get a signal that looks like it's about 1 hertz or 1 cycle per second. We could grab individual stages of this and see if we were dividing them down, right? We could put an output pin here and make sure that we took 50, divided it by 5, and got 10. We could probably do that in simulation if we made our clock cycle small enough. Let's take a look at that. Meaning we need to grab this other output here. And this would be my 5M. Oh, I can't start with a name, so 5 megahertz output there. I could do that and grab that. Actually, we could have done that as we added on stages as well, too. Instead of naming all of these pins something different, we could put them all on a bus, but let's see, I'm debating about whether I want to leave this 1 hertz clock here or not, the simulation. So I'm going to set that as top level if I hadn't already. If I run analysis and synthesis, yes, I want to save that. got my one warning about parallel compilation not being enabled, which was fine. Right. Probably not going to fare too well in this simulation, but actually I grab them all. We don't want that 1 hertz. So let's just delete that. Right. Let's set the reference clock then to maybe about 1 nanosecond. Let's make research set high the entire time. And this is my 5 megahertz sim. Running the functional simulation. All right, so starting at 1.5 and going until 6.5. So over the course of 5 nanoseconds, we get 1 complete output cycle, and we have 1, 2, 3, 4, 5 input cycles. And so that was just testing the divide by 5. We can see that the divide by 5 worked, right? And we'd seen that that worked before. So we've got our 5 megahertz signal. But being able to simulate some of the rest of these, our simulator can't handle too long a time period. Let's see, edit. Oh, that's my read only. I can't have 50 million cycles in here. And to try and read that would be ridiculous as well. We know our divide by 5 or divide by 10 works. We can, for these purposes, likely trust our math. I mean, if we were putting this in production, obviously we'd have to simulate this with other tools. Yeah, because I can't. We run this out for 100 microseconds. Reset high that entire time. And yeah, it's gonna crash. Not what I wanted. All right, so what we'll do in the next video is we'll come back and we'll actually then see what it takes to wire up the Altera board and program it to get our 1 hertz signal out of here. It'll give me time to restart Quartus and get everything set up again.